The Neuron Story by Brianna. Here illustrated in cell A, we can see that a neuron has a cell body, dendrites with a receptive area, an axon hillock, an axon branches, and the axons each have buttons. Neurotransmitters can be released into the synaptic gap. When this happens, 4 things can happen. The neurotransmitters can be washed away in the interstitial fluid in between cell A and cell B. 2, the neurotransmitters can be taken back up into cell A in a process called reuptake. 3, the neurotransmitters can be neutralized by enzymes in the interstitial fluid when the neurotransmitter binds to a dendrite on cell B. Let's take a closer look at a dendrite and a terminal button in the synaptic gap. In the button, we have vesicles that carry the neurotransmitter to the synaptic gap via a transporter. The neurotransmitter work as a lock and key method with the receptors on the dendrite on the postsynaptic membrane. As you can see, the neurotransmitter acts as the key to the receptor, which is the lock, and only certain keys can unlock certain receptors. Let's take another look at how the postsynaptic membrane can be drawn when when neurotransmitters are binding to the receptors. Here we have another view of the postsynaptic membrane and the lipid bilayer. And these are the receptors, also known as ionotropic receptors, which have ion channels. Outside of the cell, we have interstitial fluid, and inside the cell, we have cytoplasm. The interstitial fluid and cytoplasm each have different concentrations of potassium, sodium, and chloride. The amount of each ion is represented in the size of the lettering. Here is the oscilloscope reading of what is going on in the synaptic gap in the postsynaptic membrane of cell B. At a neuron is at resting rate at 70 millivolts. When a neurotransmitter binds to a binding site, it allows a certain ion to travel through the ion channel. These ions move in 2 different forms: osmosis, which goes down the concentration gradient from high concentration to low concentration, and with electrostatic pressure. When a neurotransmitter binds to a receptor, the ion channel opens, allowing, for example, sodium to freely flow from high concentration to low concentration inside the cell. When this happens, the oscilloscope reads the positivity coming into the cell and reads it by a bump on the oscilloscope reading. This is known as EPSP. When several neurons bind to binding sites on the postsynaptic membrane, several sodium ions flow into the cytoplasm inside the cell membrane, and this is called summation when there are several ESPs. At negative 65 millivolts is the threshold of excitation for sodium starting action potential. When summation reaches the threshold of excitation, This process is called temporal summation or spatial summation. All the electrostatic potential from the sodium entering into the cell membrane is collected in the axon hillock. When the threshold of excitation is reached, it sends an electrical signal down the axon. This is represented here on the oscilloscope reading. This shows the depolarization of the cell, and this represents the hyperpolarization of the cell. When all the sodium enters the cell, there is an increase of positivity or positive charge within the cell, so therefore potassium gates open up to allow for potassium to flow outside of the cell to reach equilibrium and reduce the electrostatic pressure within the cell. This is represented here on the cell where potassium reaches its equilibrium at negative 75 millivolts, where sodium reaches it at negative 55 millivolts. When action potential starts in the axon hillock, electrical charge is sent down the axon through the axon branches, where it tells different neurotransmitters to be released into the synaptic gap, where the process is started all over again.